Hey people, let's start learning for earning.
We live in an era dominated by low-voltage logic. Silicon microprocessors and programmable logic controllers, or PLCs, operate on mere millivolts. But when a facility needs to move tons of steel, pump thousands of gallons of fluid, or spin a heavy centrifuge, those delicate millivolts have to command hundreds of amps of raw, high-voltage physical power. The mechanism that safely bridges that gap is the contactor. It acts as the foundational electromechanical interface, translating the delicate digital commands of a PLC into the physical connection of heavy inductive loads. Inside the housing, the contactor is an engineered node designed to survive the thermal and mechanical shocks of high-frequency switching. It must maintain its structural integrity while operating in hostile electrical environments for millions of cycles. It is entirely distinct from a circuit breaker. While a breaker is designed to interrupt catastrophic short-circuit faults occasionally, a contactor is designed to safely make and break high-current operational circuits millions of times over its lifespan without failing. To see how it achieves this, we need to break down the physical mechanics inside the housing, analyze the severe electrical physics of switching, and map out how these units integrate into modular application circuits. Because mastering control panel design requires understanding exactly what happens inside this electromechanical bridge. This 3D cross-section reveals the physical balance driving the contactor. At the base is the fixed core wrapped in a copper coil. Above that is the moving armature with its contact pads, held apart by a central mechanical backspring. The operational sequence begins when control voltage, referred to as UC, is applied to the coil. This energizes the copper windings, generating a localized magnetic field strong enough to overcome the physical resistance of the backspring. The magnetic force pulls the armature downward. The moving contact pads slam into the stationary pads, instantly completing the high-power circuit and allowing current to flow into the motor. The moment that control voltage is removed, the magnetic field collapses. The compressed backspring instantly decompresses, forcing an immediate, rapid physical separation of the heavy silver contacts to halt the power flow. During this process, the coil draws a very high initial inrush current. As the metal core is fully pulled down inside the coil, that spike rapidly drops to a lower holding current. This precise calibration between the mechanical tension of the spring and the magnetic pull of the coil is what allows a tiny 24-volt DC signal to safely command hundreds of amps of alternating current. Once mechanical closure is established, the contactor must survive the severe electrical physics of the AC3 utilization category, the specific dynamics of switching heavy inductive motor loads. This diagram maps the electrical dynamics during a standard closing event, tracking voltage in red and current in blue. At the exact moment of closure, you see a massive surge in the current line, alongside a slight dip in voltage. This is the making current. The contact metallurgy and the mechanical closing force of the armature must be robust enough to withstand this sudden thermal and electrical stress, without the poles micro-welding themselves together. But the most destructive forces emerge during the opening sequence, visible here as a sudden exponential voltage spike. As mechanical contacts separate, the motor's inductive load violently resists the current drop, driving the voltage exponentially higher, a phenomenon known as inductive kickback. This extreme voltage spike strips electrons from the surrounding air molecules. The air itself ionizes, creating a highly conductive plasma arc that continues to bridge the physical gap between the separating contacts. To break the circuit completely, this violent plasma arc must be immediately stretched, split, and rapidly cooled into darkness. The contactor achieves this mechanically using internal arc chutes. These metal plates draw the arc outward, physically elongating it and splitting it into smaller, cooler segments, until the electrical resistance is too high for the plasma to survive. A contactor proves its engineering value by surviving this violent plasma arc millions of times without failing. A standalone contactor provides no inherent data to a control system. It requires integrated logic and feedback mechanisms to coordinate its state with the wider automated network. Modern designs rely on a modular ecosystem. The base unit acts as a central physical hub where specific logic accessories can be snapped firmly into place. This exploded view maps exactly where these auxiliary components physically integrate into the base frame. Items 5 and 8 represent the side and front mount auxiliary switch blocks, containing smaller internal contacts. Because these auxiliary blocks are mechanically linked to the main armature, they mirror its exact physical movement. This provides the PLC with a reliable, low-voltage verification loop, confirming the main contacts have successfully opened or closed. Other modules, like surge arresters, damp voltage surges at the coil, protecting sensitive PLC outputs. By snapping solid-state electronic relays or pneumatic timers, like items 7 and 10, directly onto the unit, engineers embed timing logic locally. The networking layer is managed by snap-on modules, like the AS interface, which replace discrete copper runs with a serialized data bus. These modules use Hall sensors to monitor the physical position of the armature and translate that state into digital telegrams. This allows a single 2-wire cable to carry the specific start commands and status confirmations for up to 62 individual motor starters. These modular frameworks transform the physical switch into an intelligent, networked node within the facility's control hierarchy. We can trace exactly how these physical components and logical modules interact by examining the fundamental direct online, or DOL starter. This schematic displays the standard DOL layout, separating the high-voltage three-phase power circuit on the left from the low-voltage control circuit on the right. The high power path runs straight down through the contactor's three main poles, passes through the thermal overload relay, and feeds directly into the motor. On the control side, pressing the physical start button completes the low-voltage loop, energizing the contactor coil and snapping the main contacts closed. To keep the motor running after the operator's finger leaves the button, a normally open auxiliary contact is wired in parallel. As the main armature cools down, this auxiliary contact closes alongside it, latching the control circuit and keeping the coil energized. A more complex application is the reversing starter. To reverse the rotation of a three-phase motor, you need two separate contactors working together to swap the connection of two phase lines. If both contactors were to close at the exact same time, the overlapping phases would create a violent phase-to-phase short circuit. To prevent this, a mechanical interlock block, seen here as item 2, is installed between the two units. It contains a physical wedge that makes it physically impossible for both armatures to be depressed simultaneously. Network modules build on this physical failsafe by adding electrical interlocking and software time delays, ensuring the magnetic fields have fully collapsed and the mechanical components have settled before reversing polarity. Safe, reliable industrial motor control relies on integrating advanced software programming with foolproof mechanical hardware. Operating an automated facility requires managing extreme physical forces at a massive scale. We rely on the balance of electromagnetic coils and mechanical springs to tame the high inrush currents and violent plasma arcs of heavy AC3 loads. By embedding snap-on auxiliary contacts, timer relays, and two-wire networking buses directly onto these units, that raw mechanical physics becomes a highly scalable, communicative automation ecosystem. As digital PLCs grow faster, smaller, and more complex, they still operate purely in the realm of logic. When it comes time to actually move the heavy machinery of the industrial world, the physical contactor remains the irreplaceable muscle of automation.
Namaste, my friends. Thank you for watching. Remember to like, share, and subscribe for more knowledge, and keep learning every single day.